Okay, when I look at this, I have two groupings of capacitors. I have those, they're all in a parallel branch, and then also these. These are also in a parallel branch. Notice that C7 is in parallel with C5 and 6. Now, if you don't see that right away, that's fine. Um, I can start at the big side of my battery, and I come along here, and then I come to this junction. Remember, as I said, when you have these so-called junctions that don't have anything between them, then I can collapse them all down to a single junction. As I can here with that all three of those points are the same. That is, an electron coming through the circuit, we'll see them identically. Well, they're all at the same potential, so that's why they look the same. So I can rewrite it in that circuit, have my 12-volt battery come in and break in to three different branches, where I have a 1 microfarad, a 3, and a 6, and then another 1 microfarad, and then notice that they all come back together. I can collapse those 3 points down to a single point, which I'll do here, and then I break now into two other branches, where I have a 2 and a 2, and then this, even though it makes this bend, this capacitor is still in parallel with these two. In fact, I could just move this capacitor over to here if that makes you feel better. Sometimes students get confused by this. They think these two are in series, or these three are in series, but they're not. You can tell because there's a junction in between them. Okay? So then I have the 2 and the 2 and the 1. And then that all comes back together, and it goes back to the battery. Let me write in these numbers here. I have 1 microfarad, 3 microfarads, 6 microfarads, 1 microfarad, 2, 2, and 1. Really recommend you either write C equals the number, or you write the units, so you can keep them straight, keep them separate from the voltages that you'll write later. Okay, so now that 3 and the 6, these two will become a 2 microfarad, and these two will become a 1 microfarad. In fact, I'm going to go ahead and do this a little bit differently, where now I have, I'm just going to skip a couple steps, where I jump right ahead to the circuit that has a, what's that, 1, 2, and 1, a 4 microfarad, and a 2 microfarad. Volts. You see what I did there? I said the 3 and the 6 is 2. That's 1 over 3 plus 1 over 6 is 2. And I said the 2 and the 2, the equivalent is 1. 1 over 2 plus 1 over 2 is 1. And then I said 1 plus 2 plus 1 is equal to 4. And then 1 plus 1 is equal to 2. Go with me on that? I skipped a step. If you want to draw that intermediate circuit, you can. Are we okay with that? Okay. So now that I have the 4 and the 2, I'll go ahead. You might know what those voltages are, but I'm just, even if you don't, I'm going to go ahead and do this. I have a 4 and a 2, 1 over 4 plus 2, 4. That's going to be 4/3 microfarads. That's the equivalent. I think I asked the equivalent capacitance, right? Isn't it 4/3? I did that right? So yeah, I asked for the equivalent capacitance, and that's going to be 4/3 microfarads. Then I can ask what is the charge? And the charge, Q equals CV, is going to be 12 times 4/3. That's 16 microfarads. So that means I have microcoulombs. I have 16 microcoulombs and 16 microcoulombs. Then if I want to know the voltage is equal to Q divided by C. So that 16 over 4 is 4 volts. 16 over 2 is 8 volts. You see how I did that? I found the charge on this capacitor. Because capacitors in series have the same charge, that's also the charge here and here. Then I found the voltage, which is Q over C. 16 over 4 is 4. 16 over 2 is 8. However, I could have just said, well, these are two capacitors by a factor of 2 difference. They have to add up equal to 12. The voltages do. So it has to be 8 and 4 the small capacitor is going to get the big voltage, and the big capacitor is going to get the small voltage. Remember, that rule is switched for resistors: big voltage, small resistor, small voltage. But if you don't know how to do that, that's fine. Okay? And then I can start to write some of these voltages over here, so that the 2 microfarad right here is the equivalent for that, so that's 8 volts. And then the 2 microfarad capacitors also have 8 volts across them. That means that each has what voltage? 4 volts. Each of these has 4 volts and 4 volts. Let me just address that here. So this capacitor is the equivalent for this little segment. It has 8 volts. So each parallel branch also has 8 volts. 8 volts. And then across these 2 microfarad capacitors, also 8 volts. However, they're identical, so they split up the voltage evenly. So I have 4 volts and 4 volts on those 2 capacitors right here. What's the voltage on this capacitor? On this capacitor? 4 volts, because it's the same as what I have over here. This is the equivalent of this parallel branch. So I have 4 volts. And what about this one? 4 volts. And this one's a little more complicated. We'll address it. 4 volts and 4 volts. I don't know if I asked for that one. Let's see, what was C3 and C6? C2 and C3. I did not ask for that, but we'll address it anyway. So we have all the answers. Let me just write down the answers here. So the charge on C4 is this capacitor. Q is equal to CV. So that charge is equal to 4 microcoulombs. I just did 1 microfarad times 4 volts. And then the voltage on C6 was this voltage. So that's equal to 4 volts. Can we just address these 2 capacitors just to do this again? Because this might come up on your test, where you face a situation where you have 2 dissimilar capacitors that have a voltage that is not evenly distributed itself. There's not like a 4 and an 8 or a 6 and a 3 or something like that. So what's the voltage across that 3 and 6 microfarad capacitor? 4 volts. I know that because this is the equivalent, and I have 4 volts here, here, and then across these 2. So I can think about that as a separate circuit. I'll draw it down here, where I have an imaginary 4-volt battery connected to that's not a resistor, to a 3 and a 6 ohm 3 and 6 microfarad capacitor. You'll see what I'm doing? I'm just imagining a smaller circuit. The 3 and the 6 have 4 volts across them. So I can draw that as an equivalent, which is 2 microfarads, 4 volts. Then that means that it's going to have a charge of 8 microcoulombs. Also, 8 microcoulombs, 8 microcoulombs over there. So then that means that the voltage is going to be Q over C. That's 8 divided by 3 volts. And 8 divided by 6, or 4 divided by 3 volts. So those are my voltages across the 3 and the 6 microfarad. I'm pretty sure you have a situation on your circuit for tomorrow where you have to find the voltage on one of those dissimilar capacitors. That's probably the hardest part of that particular problem, because it's embedded, and you first have to find the voltage across that branch, and then you have to split it between those 2 dissimilar capacitors. So you really have to go through the whole process of finding the equivalent, finding the charge, and then setting that charge for each capacitor and calculating the voltage. It's not hard, right? I said the rules aren't difficult. It's just applying them all consistently can be tricky. Okay? All right, so that's that one. That one's probably the most difficult I find that students have trouble with. So I would, if you're finding something to practice at the last minute, that's probably it. That students have probably the most difficulty with it. The redrawing it, and then also just going through it. There's a lot of capacitors there to deal with. Remember, when I have these junctions that are spread apart like this, these are not really separate junctions. These are still the same junction. So I can collapse them down to a single point like this, And then also when I have a capacitor like this where it's sort of around the bend, that's still in parallel with this branch because they're separated by a junction. All right, let's look at this one. This one's easier. So I'm going to start with the 3 and the 6. It's in parallel. The 12 volt, I'll draw the 1 ohm, and then the 3 and the 6 is 2. So this is 2 ohms. I'm going to go ahead and combine it with that 1 ohm. So I'm going to have another 3 and another 6. 3 ohm, 6 ohm, and then I go back to my 12 volt battery, and then that gives me a 1 and a 2 ohm resistor. 12 volt battery. So the equivalent then is going to be 3 ohms. It doesn't ask for that. I don't think I asked for it on the exam either. But it might be useful for you to find the equivalent, or at least to simplify that circuit, at least down to that next to last step. Then I want to know the voltage on each. Now, the rigorous way, the way they'll always work, is I ask what is the current here. I is equal to V over R. That's 12 over 3, or 4 amps. So I have 4 amps there. That means I have 4 amps here and 4 amps here. Right? Yes. Okay. So 4 amps I have on each of those capacitors. So that means I have V is equal to IR. So I have 4 volts and 8 volts. Okay, but if you're clever about it, then you could have stopped here and said, well, I know I have 4 volts and 8 volts for reasons that we said before. But if you're not quite getting that right now, you need to go to this step, calculate the current, and then calculate the voltage across each resistor. You might have to do that anyway, depending on what those resistors and voltages are, because they don't always split up. Just like we had with the situation that was down there with the 3 and the 6 and the 4 volts. Okay, so now I know this is 4 volts here. Both of these are 8 volts. Here I just copied this 4 volt up to here. Here this equivalent resistor was 8 volts. So each of these constituent resistors are also 8 volts. And then I had a 2 and a 1 right here that have 8 volts across it. So just like we did before, we have to go through that process because, well, it's not obvious. So I'm going to draw a little circuit that just represents that part. That's 2 ohms and 1 ohm connected to this imaginary 8 volt battery. That is a 8 volts with a 3 ohm resistor. That means I have a current of 8/3 amps. 8 divided by the equivalent resistance of 3 is 8/3. That means that I have a voltage. I'm doing voltage in green. That means my voltage is going to be V equals I divided, V equals IR. 2 times 8/3, which is 16/3 volts, and 1 times 8/3, which is 8/3 volts. 16 plus 8 is 24, divided by 3 is 8. So that adds up to give me the total of 8. All right, so let's just see what I have here. I did them all. The voltage across R2, that's 8 volts. And then the voltage across, oh wait, no it's not. What is it, R2? What is it? No, 16/3. 16/3, yeah, 16/3. That's this value. And then the current through R1, well, that's just this current, 4 amps. That's the total current. Okay? Well, that one seems hard too, doesn't it, Ava? Yeah, of course. Yeah, I accept decimals. Yeah, 5.3 is fine. Yeah, keep a couple sig figs. I'm not going to grade you on sig figs, but you know, don't give me 12 decimal points, but don't give me 1 integer either. A decimal place is fine. Any other questions about that? Okay. And then this one, This one's probably the easiest, I think. It's just sort of the most cut and dried. As long as you know those rules for the batteries and the resistors. That is, when I'm going in a battery in this direction, that's a positive change in potential. If I'm going in the opposite direction, that's a negative change in potential. If I have a resistor and I have a current going in that direction, if I'm going in this direction, that is negative IR. If I'm going in this direction, that's positive IR. I should probably tell my wife this stranger is coming. So sorry, y'all. Okay, I think y'all know those rules. We're good? All right, so I pick my loop carefully, because notice that bottom branch right here doesn't have a resistor in it. Oh, I have to choose the direction for my currents first. So I'm going to choose, doesn't matter what I choose, randomly. And then I choose my loops. I'm going to do, gosh, which loops am I going to do? Big and bottom, right. The big one because it includes that bottom part, and the bottom because it also includes that bottom part. Let's do the bottom first. I'm going to start here and go in this direction. So I have plus 2, minus 8, plus 5, I2. Be careful that your signs are correct and that your currents are correct. Because notice that I went from I3 to I2. The 5 ohm resistor has I2 in it. Also be careful, I've seen this mistake a lot, where students will write 8 volts, but then they'll write 8 times I2. They sort of look at this as a resistor and think they need to multiply times the current, but you do not. Make sure your signs are correct and that your currents are labeled correctly. That's negative 6 plus 5I2 equals 0. So I2 is equal to 6/5 amps. Came out positive. That just means I chose my direction correctly. Then I can do the big loop. I'll start at the same point. Plus 2 minus 2I1 minus 3 equals 0. Then I can solve that. That's negative 1 minus 2I1 equals 0. So I1 equals to negative 1/2. All right, and then finally, I can do a junction rule. I'll just pick a junction. I like to draw my arrows closer, so I just see what's in and out. When I do that, I see clearly that I2 is in, and I1 and I3 are out. So I2, I know, is 6/5 equals to I1, which is negative 1/2. Keep that negative sign until the very end, plus I3. And then that's 6/5 plus 1/2 equals I3. That's 12 tenths plus 5 tenths, 17 tenths. So that's 1.7. So I3 is 1.7. It came out positive. That means I chose it right, correctly. I2 was 1/2 amp, or 0.5. I chose it to the left. That means it's going to be to the right because it came out negative. And then I1 is, I2 is 6/5, I'm sorry. That's 1.2, or 6/5. That's I2. It came out positive, so it's to the left. And then I1 is 1/2 an amp. I chose it to the right, but it came out negative, so it's to the left. Yeah, Ben?
Real quick, how do you know what's in and what's out for the...
Oh yeah, so right here, when I do the junction rule, when this current is going into the junction, this current's going out, and that current's going out. It's going away from the junction. Did I do that right?
Yeah.
I2 is in, yeah, I1 and I3 are out.
How do you know if I3 is in or out if you don't know the sign on it yet, since you're solving for it?
It doesn't, yeah, so how do I know? I don't know the sign. I don't know the actual direction of I3 yet. But it doesn't matter whatever direction you chose, you assume it's correct until the very end. okay? Because all the other equations rely upon your chosen directions, and if you start changing directions, then it's not going to work out right, because your equations will not be consistent, just like in Elizabeth. Okay?
So you don't need to like flip the directions of the arrows when you see if it's like negative or positive?
Absolutely not. Do not flip the directions of the arrows until they spin. When you're recording your answers, that's the and that's a common mistake that people make, is that they flip the direction. Like when they, oh, this is negative, I chose it wrong. You didn't really choose it wrong, it's just, oh yeah, it's just not correct. You didn't do anything. But listen, I went this direction just because that's what I did with the bottom loop.
So you just go the same way with all of them?
It doesn't matter what direction you go. I mean, it helps if I have that, I can go the same way, just because then this is still positive too.
So just stay the same way?
Sure, yeah. Like start in the part where you need to be, and just go the same direction. But it doesn't matter what you do. If that's easier for you, then do it that way. Plays? All right, thank you.
Can you explain how you got the in and out on this side? I couldn't see.
Yeah, so in, I2 is going towards the junction, that's in. I3, I1, and I3 are both going out of the junctions. And then also notice that I have this arrow up here. I1, the current I1 goes in that part of the circuit. It's in that direction, it's in that direction, it's in that direction. I2 goes in that part of the circuit, it's in those directions. And then I3 is in that part of the circuit, going in those directions. So I can trace these arrows back to the junction where I want them to be, and I see it going in, and then these two are going out.
Does it matter where you choose the junction?
There are only two junctions, here and here. This has I2 equals I1 plus I3. If you do it over here, you have I1 plus I3 equals I2. So no, it doesn't matter. They're mirror images of one another. Okay, that answer your questions? Yeah, you two, please. You're good. Okay. All right. A lot of circuits. I mean, it's all circuits on the free response. So if you like circuits, you're welcome. If you don't, I'm sorry. But they're important. Y'all, I've been reading this book, Smart. A couple of y'all are reading it for honors credit. Rocks my world. The role that electricity plays in the body is just fascinating. In the nervous system, in other creatures, like marine creatures, or not just marine creatures, but all sorts of creatures, that electricity is just such a part of our body, the nervous system, and then like for animals, their defenses, and various other, their like detections and how they detect things. Fascinating. I was saying that, if you're going to medical school, you're going to see a lot of electricity, because it's important for the nervous system. Or vet school, marine biology, it's important. Alright, what else do I want to do? Wait. Alright, now on screen 21. Okay. So the one that produces the most power is the one that either has the most voltage or the most current. So since I'm not ranking anything, I'm not comparing one or the other, I just ask which has the most voltage or which has the most current. Which of those do you think is the easiest answer, easiest one to answer? Most voltage or most current? I think the current is easier to answer. We've actually had that question. We've had it in the concept test. Let's think about it, okay? If I have a current coming off this battery, say I have, I don't know, 12 amps. I don't know what it is, but let's just say 12 amps. Here, that current comes to two identical resistors, and it's going to split into 6 amps and 6 amps. They'll split up, go through the resistors, 6 amps and 6 amps, and then they'll come back over here. So I'm going to split into equal currents. Then here, which part of the circuit is going to get the most current? The top or bottom? The bottom, because it's a smaller resistance. In fact, it'll get 8 amps down here and 4 amps up here. Because this has twice the resistance, it'll have half the current. So I have 6, 6, 8, 4. Which has the most power? R5, right, because power is equal to I squared R. You don't even really need to know that equation. You just need to know more current, more power. More voltage, more power. So R5 has the biggest power. I think that's probably the easiest way. And there are some, like there are, I think at least two questions, maybe more, that are those sort of conceptual type questions where I'm asking about voltage and charge and current, or even like ranking questions like this. Let's do this one too. So this one is asking you to rank them from bright to least bright, which would also be, you know, the voltage or the current, which one has the most voltage or most current. I think in this case, it's actually probably easier to think about the voltage. And then I also said note that they had different voltages on these batteries. If you've been practicing the old exams, you've seen variations on this question. So if I have A, the light bulb A would have a voltage V over 2. The light bulb B would have a voltage of 2 volts divided by 3 ways, 2V over 3. And then the light bulb C would have a voltage of, well, 2 volts divided by 2, or V, and then D would have 2 volts. I'm going to set back what I did here. So this has a voltage V. These two light bulbs split that voltage evenly. So I get V over 2 and V over 2. This one has 2 volts. These 3 light bulbs split it evenly into 3 parts. So I get 2 volts divided by 3, or 2/3 volts. And then here I have 2 volts, here divided by 2, so it's V, and then this gets the full 2 volts. So if I were to rank them from brightest to least brightest, it would be D, followed by C, that gets rid of these two, followed by, what's bigger, V over 2 or 2/3 V, so followed by B, followed by A, so B would be the right answer. Yeah. I would expect more than 2 or more questions that are similar to 10 and 11. All right, good question. Kaylee?
Number 5 on 24.
Okay. Make sure my wife's not abducted or anything. Oh, looks like she's okay. Number 5? Okay, so this was a current/power question. I don't give you many of those, but you'll have one that'll either be just power or current or some combination of the two. As with most of these, I like to really write down what I know. So the power here is 1,000 watts. The voltage is 120 volts. And then I want to know what is the charge equal to. And I know that the time is equal to 1 minute. But of course, that's not SI units, so I'm going to go ahead and convert that to 60 seconds. And then I know that P is equal to VI. That's on my equation sheet. I have those other equations for P, V squared over R, and I squared R, but I don't know what R is, so it doesn't really help me. I'll just write P equal VI. And then also I know that Q is equal to I times T, or I think I wrote it as I equals Q divided by T. So first I have to figure out the current. 1,000 watts equal to 120 volts times I. So that I is equal to 1,000 divided by 120. I know what that is right off the top of your head. 8.3. That's equal to 8.3 amps. Then I find out what my charge is. That's 8.3 amps times 60 seconds. 500, I guess? Yeah, 500. Okay. You will definitely see, I know for a fact that you'll see one with Q equals IT. I don't remember if it had power as well. I don't remember that. Okay. Just knowing the definitions. Yeah, Katie? 16 on spring 21.
Okay. You do have one of these. It's not this complicated, but you will have one of these though. It's junction rule. Incoming currents equal outgoing currents. I want to know probably the easiest way to find it is to examine this junction. Notice there are two junctions here. There's that junction and the one up top. I said the easier one is here because I already know one of these currents. You can find it from this one. I'll show you. But here, I can look at that junction. If I knew what current was happening here, then I could determine this current. Whatever incoming is equal to the outgoing currents. So I need to know this current. But look, I know this is coming in and this is going out. Let me draw those arrows up closer to that junction. I have 4 amps here and 12 amps here. That means I have to have a current of 8 amps right there. And then if I have 5 amps going in this direction, that means that this current has to be, what? 3 amps. So that's the answer, 3 amps. You can get it from the other way. Oh my gosh, it's a little more difficult. No, we don't want to do that. You're not going to have 2 ways to find it. And on yours is simpler. But that's the simpler way to do it. Yeah, Katie?
So you don't need to use all of the amps?
What do you mean all the amps?
Like they don't all connect to where you find the answer that way?
Like you don't need to use the 6, is that what you're asking?
Yeah, like you don't need to use...
You don't need to use the 6, right. But there is a way to find it using that lower junction. This junction right here. I think that's right. I think you have to find this current, and then this current, and then this current. It was actually fairly difficult. This is the better junction. Yours isn't this complicated. Okay. Yours is only going to have one way to solve it. I'm pretty sure that service consistent. Should be. Okay. Is that it? Oh, I asked that. Did you ask it? Yeah. Is that good? Russ? 15 from spring 19. I have to admit that I actually forgot the help session. I'm really sorry. It wasn't that I just had something to go do at home, because I've been grading like a madman all day because I had 50 exams, which they all got posted today. Thank you. Yeah, you're welcome. Which one? 15? And so I rode my bike home and I said hello to my wife and saw my dog and petted her for a few minutes, and then one of you sent me an email. Are we having a help session today? Yeah. And so I rushed. Yeah, don't worry about this one, Corrales.
No, that's not it.
Okay.
I think that exam one.
Which one you got?
Got it written at the top of the page.
Oh, yeah. Can I just see what the question is? Can I, I'll bring this back to you. Or here, no, Corrales. Oh, it's spring 19, number 15. I'll just pull it up. There are some exam 1 questions, so beware of that. There's a packet of practice exams on the Canvas site. And I circled all the questions. Okay, here it is, number 15. A parallel plate capacitor initially has a potential difference of 10 volts, and it is then disconnected from the charging battery. When you see this, you think the charge is constant. If I'm disconnecting from the battery, whatever charge that battery put onto that capacitor is remaining the same. If I'm staying connected to the battery, what's constant? The voltage, right? If I stay connected to the battery, the voltage is constant. But here, if I disconnect the battery, the charge is constant. And then Q is equal to CV, and then C is equal to epsilon naught A over D. What I'm doing here is we are doubling the area, and I want to know what is the new value of the voltage. If I double the area, I double the capacitance. If I double the capacitance, if the charge remains constant, then I'm halving the voltage. So whereas the voltage was 10 volts, now it's going to be 5 volts. And I talked about this in class. That's sort of what happens when you, like, if you have a keyboard and you press a button, you're actually changing the dimensions of your capacitor. With that, you're actually closing the separation, and then that changes the voltage, which sends a signal to your computer and tells you, oh, you need to press the B key or whatever. So let me step back through that. If I'm disconnected from the charging battery, the amount of charge is constant. If the amount of charge is constant, if I double the area, that doubles the capacitance. And if I double the capacitance, then I have to halve the voltage. When you see a problem like this, I don't remember if you are, probably so, write out both equations. Ask yourself what's remaining constant. Just draw a little line on it like I do here. And then ask how does the capacitance change? And when I change the capacitance, what does that do to the other variable? Okay? That's kind of a difficult question. You have to really think about what's going on with the equations and what's constant and what's changing. It's not an easy question. The good news is there's only a couple of different variations of it. So if you practice with 2 or 3 variations, you're probably okay. All right? Well, other questions? Abby? Okay. On exam 2 or 1? 2. $24. I actually saw Abby on the way home, my first run. I'm ringing my bell, like, oh, hey, Abby, and I guess she was headed over here, but not me. I was headed home. So sorry. All right, good. So this is one where you're comparing the brightness of a bulb. And in this case, you actually do need to know the equation. Probably easier for us to use this equation, V squared over R. The reason I say that is because all these have the same resistance. So I'm not going to use this equation, P equals VI, because the resistance isn't in it, because each bulb will have a different voltage and it will have a different current. So this isn't very helpful to me because both V and I are different, and it's just, I could do it, but it's more difficult. But here, it's fairly easy for me to say that the voltage of this one is twice the voltage of this one. You'll see what I did? I know I have V across this bulb, and then across these 2 bulbs I also have V, but they split it evenly. So I have V over 2 and V over 2. I want to know, how does the brightness of bulb A compare to that of B? Well, bulb A is, I like to ask myself first, is it brighter or dimmer? Is bulb A brighter or dimmer? It's dimmer. So I can get rid of these 3 options, and then if it has half the voltage, that means it has 1/4 the power. So it's 1/4 as bright. Power is always brightness. Brightness is directly correlated with power. Abby, is that okay? Yeah. There are other types of questions like that.
Can you do 14 on the same?
Mm-hmm. I like help sessions. I hate that we don't have eight help sessions. What is the current in this current I in this circuit? So this is similar to what we did before, and you will have a question like this that will require you to step back at least one junction. So if I know this current, then I can answer the question of what is I, because it'll just be 8 plus whatever that current is. But look, I know that this is 3 amps, and this is 5 amps. That means that this current has to be 8 amps, which means that I has to be 16 amps. That's the answer, 16. Or I could say, if I know this current, then I could find I. Well, this current over here, it should be 13 amps. See, because 13 is equal to 8 plus 5. So if I have 13 amps here, and 3 amps here, then that means that this current has to be 16 amps. So either way you could do it going into that junction. Here's this similar, the question you'll have, except there's only really one junction that you'll need to, there's only one way to solve it. Okay? All right. What else? Yeah.
Our response is gonna be like I1 equals I2 equals I3. It's not gonna be like square 24 where it has like just less.
That's right. So it has, I have I1 equals blank, left or right or up or down, depending if it's portrait or landscape.
Okay.
And then, yeah. And there'll be 3 questions. What is I1? What is I2? What is I3?
Okay.
All right. All right. Y'all have a great day. Oh, I need to make sure I get your name. So don't leave. Hold on. Just pause.